Hey everybody, this is Mr. Bortnick for AP Calculus AB. This is Unit 6, Integration and Accumulation of Change. Today we're doing the Chapter 6 End of Unit Review. We're focusing on Section 6.6 through 6.10 and 6.14. In this review, you're going to want access to your graphing calculator, that TID3 or TID4, and a reminder when using those calculators that we should always be using radian mode, and if we're rounding, round to 3 digits after the decimal place. Enjoy today's review. Welcome to the end of Unit 6 review, which was on integration and accumulation of change, talking about lessons 6.6 through 6.14. As usual, the reviews do not cover all material from lessons. We'll hopefully remind you of key points. To be prepared, you must study all the packets from Unit 6. That's the best way to prepare. All right, so we've got some mixed review we're going to go through. Let's do it. Find the value of the definite integral. So in cases like this, let's try to figure out what to do first. I'm going to try to rewrite this term first so that I can apply my my power rule for it. And so let's do that. So we've got the integral from -2 to -1 of x to the -2 power plus x squared minus 5x dx. And I'll get rid of that little. So now if we take the antiderivative, because I have limits of integration, I'm going to put this sort of bracket here to show that I've taken an antiderivative. I'm going to add 1 to the exponent. -2 plus 1 is -1. We divide by that new exponent of -1. X squared, we're going to add 1 to that 2, so that's x cubed, dividing by that new exponent. And then we've got a minus 5x squared over 2. We then need to plug in our limits of integration using our fundamental theorem of calculus. But again, I'm going to simplify this first. I don't really like having negative exponents before I do that. So this is the same thing as -1 over x plus x cubed over 3 minus 5 over 2x squared from -1 to -2. Now, if we do that first FTC, or that FTC that we've got here, plug in the -1 first for all the x's, then we're going to subtract, then we're going to plug in -2 for each of those x's, and then we simplify, and then we're going to be done. So this is going to be -1 over -1 plus -1 cubed over 3 minus 5 over 2 times -1 squared. Then we need to subtract our, We've got -1 over -2 plus -2 cubed over 3 minus 5 over 2 times -2 squared. So all of this, so again, what have we done? We rewrote it first. We took the antiderivative, then we simplified it, plugged in -1, we're subtracting, we plugged in -2, and then we just need to simplify. If you have a calculator, if you don't have a calculator, I'll just sort of skip to this and just say this is going to be 31 over 3 if you end up doing that problem. I would, if you're doing it without a calculator, you're just going to need to find a common denominator for each of these. Ends up being 3 when you simplify. So nice. Let's talk about number 2. We've got the integral from -1 to 8 of x to the 2/3 minus x. This is already set up pretty nicely for us to use our power rule. So let's do that. So this is going to be equal to the integral of x to the 2/3 plus 1. That's going to be 5 over 3 divided by the new exponent of 5 over 3 minus x squared over 2. And then we keep those limits of integration. I'm going to simplify. So this is going to be, since we're dividing by that fraction, I'm going to multiply by the reciprocal instead. That's going to be 3/5 times x to the 5 over 3 minus x squared over 2 with the 8 and the -1. Now we're going to do our fundamental theorem of calculus. We're going to plug in 8 for all the x's. We're going to subtract, and then we're going to plug in -1 for all of the x's. That's going to be equal to 3/5 times 8 to the 5 over 3 power minus 8 squared over 2 minus 3/5 times -1 to the 5/3 power minus -1 squared over 2. If we do that, if we simplify, this looks like this is going to end up being what? 96 over 5
minus 64 over 2 minus, negative 3 over 5 minus a half. And then, so then we want to find a common denominator if we can. We've got 96 over 5 minus 32 minus, we want to have some 10s here, so negative 6 over 10 minus 5 over 10. So that's going to be equal to, we want these all over 10, so 192 over 10 minus 320 over 10. And then we've got minus negative 11 over 10, so it's going to be plus 11 over 10. So 192 minus 320 plus 11, that's going to be negative 117 over 10 for that integral here. Nice. Let's talk about number 3, trig functions. This is already set up pretty nicely. Let's take the antiderivative. So the antiderivative of x is x squared over 2. The antiderivative of negative sign is going to be positive cosine of x. We keep our limits of integration. Next, we're going to do our fundamental theorem of calculus. We're going to plug in pi to both x's. We're going to subtract. We're going to plug in 0 to both x's. So that's going to be pi squared over 2 plus cosine of pi minus 0 squared over 2 plus cosine of 0. And so that looks like that's going to be pi squared over 2. Cosine of pi is going to be negative 1. And then we've got 0 plus cosine of 0, which is positive 1. So we have pi squared over 2 minus 1 minus another 1. So then our answer here is pi squared over 2 minus 2. That's going to be problem number 3. Sort of a reminder for this, you might be thinking, when do we need to use C's? How do you know? I don't need C's for these because these have limits of integration, right? If they didn't have limits of integration, if they were indefinite integrals, then we would have these plus C's for it. And we'd have to have the plus C's. Nice. Let's talk about number 7. Number 7, we've got something that looks a little bit more complicated. So can I take the integral the way it is? No, I got like x times the square root. I got an inside part. So really, the fact that I see an inside part is telling me, maybe I should try u-substitution here. Let's call the inside part u. And so if we take the derivative of both sides, du dx is equal to negative 2x, which means that du is negative 2x times dx, and that dx is du over negative 2x. So I've got my u. I've got my dx, which I should use a different highlighter color. That's going to go right there. Let's substitute in and see what happens. So this is the equal to the integral. Oh, we also don't want to forget our limits of integration since this is a definite integral. When x is 1, right, if we're looking at our two limits of integration, 1 and negative 1, when x is 1, u is going to be equal to 1 minus 1 squared, that's 0. And when x is negative 1, u is going to be equal to 1 minus negative 1 squared, which is also 0. So that means that if I do this, the limits of integration are going to be from 0 to 0 of x times the square root of u times du over negative 2x. Now at this point, I can see some stuff's going to cancel, but I actually just don't care because I notice that my limits of integration are the same, right? These came from over here. And we know that when the limits of integration are the same, it doesn't matter what the integrand is, that this integral is always going to be equal to 0. Because we know that at the heart of it, an integral is finding the area between the curve and the x-axis between the two given limits of integration. And if the limits of integration are the same, there's no space, there's no area that I can actually be finding. So that's my answer for this one, and that's nice because I don't have to go any further than that once I see those limits of integration are the same. Number 8, we've got a lot of stuff happening right here. But I notice that this is a sine of 2x divided by cosine of 2x quantity squared. So since this whole cosine of 2x is being squared, I'm going to make that my u. My u here is cosine of 2x Again, that's like technically like this is being squared. That means the same thing. So u is equal to cosine of 2x. Next, let's take the derivative of both sides. Du dx is equal to, by the chain rule, technically, 2 or negative 2 sine of 2x. And then if we multiply by dx on both sides, du is equal to negative 2 sine of 2x dx. So dx is equal to du divided by negative 2 sine of 2x. All right, we got our u. We've got our dx. Let's substitute in, and I guess we also need to find our limits of integration. So let's do that. When x is equal to pi over 6, u is going to be cosine of 2 times pi over 6, which would be pi over 3. Cosine of pi over 3 is going to be 1/2. So u is going to be 1/2 in that case. And then if x is equal to 0, u is going to be equal to cosine of 2 times 0. Cosine of 0 is going to be equal to 1. So I've got new limits of integration, 1/2 and 1. And this is interesting because 1 is our lower limit of integration and 1/2 is our upper limit of integration. And normally we want the bottom number to be lower, but that's not the case here. So maybe we'll use some properties here coming up. We've got sine of 2x divided by u squared times du over negative 2 sine of 2x. Whew. So all of this is this right here. Maybe a little bit tough to see. Sorry about that, but that came from right here. But what do I notice? I notice immediately that sine of 2x. Notice that sine of 2x and sine of 2x are going to cancel. I'm left with this negative 2 in the denominator, which I'm going to just pull outside in front as a coefficient, as if it's like a negative 1/2. So I have negative 1/2 times the integral from 1 to 1/2 of 1 over u squared du. 1 over u squared du. Next, before I even take the antiderivative, again, I really want my lower limit of integration to be smaller than this. So I'm going to just flip these limits of integration. We know that when we do that, one of our properties of integrals says that if you switch the limits of integration, that it makes the whole integral statement negative. So that's going to make this a positive 1/2 on the outside, going from 1/2 to 1 of 1 over u squared du. And actually, I don't want to write that as 1 over u squared. I'm going to say that that's u to the negative 2 du. And let's take the antiderivative. So that's going to be u to the negative 1 over negative 1. And that is negative 1 over u, if we get rid of that negative exponent. So by the fundamental theorem of calculus, if we plug in, that's going to be negative 1 over 1 minus negative 1 over 1/2, which I guess I'll go, just running out of room, so might as well go over here. So we've got negative 1/2 times negative 1 over 1 is negative 1, and then negative 1 divided by 1/2 is negative 2, so it's negative 2, so that's plus 2. So that's negative 1/2 times 1, which is negative 1/2. That's going to be our answer for problem number 8. Doing some u-substitution in this problem, having to change our limits of integration just because we changed our variables. Let's try number 9. Number 9, what do we see? Well, we see the integral from e to e squared of 1 over x natural log of x. Let's do this. Let's make our u the natural log of x. If we take the derivative of that, du dx is equal to 1 over x. If I'm going to get dx by itself, that means that x times du is equal to dx. So I don't want to use orange. So u is the natural log of x. We got that. We got the dx, which is x du, and let's see what happens. So this is going to be equal to, oh, we need to change our limits of integration. Don't forget about that. I almost did again. So when we've got x is equal to e squared, u is going to be the natural log of e squared. The natural log and the e are inverses. They're going to cancel, so that means that u is 2. And then when x is equal to e, u is equal to the natural log of e. Again, ln of e are inverses. They cancel, so u is going to be equal to 1. So our new limits of integration here are going to be 1 and 2. And from there, we've got 1 over x times u times dx, which we said was x du. So what happens? Well, we notice that our x and our 1 over x are going to cancel each other out. So this is equal to the integral from 1 to 2 of just 1 over u du. And we know that the integral, or the antiderivative of 1 over u, is the natural log of the absolute value of u. And so by our fundamental theorem of calculus, we're going to plug in 2 for the u, we're going to subtract, and then we're going to plug in 1 for the u. So this is equal to the natural log of the absolute value of 2, or just ln of 2, minus the natural log of the absolute value of 1, which is just 1, and log of 1, or natural log of 1, is 0. So our answer here is going to be just ln of 2 for problem number 9. Great. Number 10. All right, what do we know? We got some properties of integrals. If the integral from of f of x dx from negative 5 to 2 is negative 17, and from 5 to 2 of f of x dx is 4, what's the value from negative 5 to 5 of f of x dx? Well, one of our properties of integral says that if I want the integral from negative 5 to 5 of f of x dx, that I can break that up into 2 adjacent integrals. So I could go from negative 5 to 2, which I see right here. That's nice. But to finish this, to go from negative 5 to 5, I got to go from negative 5 to 2, and then I got to go the rest of the way from 2 to 5 of f of x dx. So we can see that, we're trying to find out what this is. This is what we want. I don't know. We know that negative 5 to 2, looking at this, is negative 17. And then what would the integral from 2 to 5 be? Well, we don't have that, but we do have from 5 to 2. And we know that if we want to flip this, we want to switch those limits of integration, we can just make this integral negative. So instead of being 4, we're going to make that negative 4. So this negative 5 to 5 is going to be equal to negative 17 plus negative 4. Hey, that's going to be negative 21. That's our answer A for problem number 10. Let's flip over to number 11. Find the following definite integrals, or indefinite integrals. Here's one where we can simplify. We see that this x is dividing each of those things. This is the integral of x squared over x minus x over x plus 5 over x dx. So that's going to be the integral of x minus 1 plus 5 over x dx. And so that's going to be x squared over 2, taking that antiderivative, minus x plus 5 times 1 over x, so that's 5 times the natural log of the absolute value of x plus c. That's going to be our antiderivative here, our indefinite integral, since they have no limits of integration. Don't forget your plus c. We know that we need a plus c because there are no limits of integration on this. And of course, they told us it's an indefinite integral. Next, we got a trig function. Hey, what function gives us, when we take the derivative, has secant x tan x? Oh yeah, that's just secant x. If we take the derivative of secant x, we get secant x tan x. So the antiderivative of secant x tan x is just secant x. And then we add that plus c, and we're actually done. It's finished. What about number 13? Well, the antiderivative of e to the x is e to the x. And the antiderivative of 2 to the x is 2 to the x divided by the natural log of 2 plus c. Boom, we're done. Nice that we've got these properties of antiderivatives memorized. All that work that we did back in chapter 2 and chapter 3 is really paying off. Number 14. Let's rewrite this one. this looks like the integral of 1 over x plus x to the negative 3 dx. I didn't rewrite this one because I'm always on the lookout for 1 over x because I know that's going to be a natural log when I take the antiderivative. But this, because there's a cubed there, that I did rewrite it. So this is equal to, when I take the antiderivative, the natural log of the absolute value of x plus x to the negative 2 over negative 2 plus c. So that's the natural log of the absolute value of x minus 1 over 2x squared plus the c. So that is going to be our answer for problem number 14. Number 15 here, how can we do this? I'm going to make this an x to the 1/2, and then I'm going to distribute to both of these. So this is going to be equal to the integral of x times x to the 1/2, so that's x to the 1.5, or 3 over 2. And then we've got minus 4, so 4x to the 1/2 divided by x, so that's divided by x to the 1/2 dx. And so if I want to simplify, x to the 3 over 2 minus 4x to the negative 1/2 dx. This, no natural logs are going to be needed, luckily for us. So we add 1 to the 3 over 2, that's x to the 5 over 2. We divide by the 5 over 2, minus 4 times x to the negative 1/2 plus 1, that's positive 1/2, divided by that positive 1/2 plus the c. And so that's going to be 2/5 times x to the 5 over 2 minus 8 x to the 1/2 plus the c. That is problem number 15. 16 and 17 we're going to skip because those were topics from 5.10, or rather 6.10, which we did not do in this chapter. This one looks like it's going to be one we're going to use division for to simplify. This one we could do with completing the square. But again, those are not topics that we're going to be covering this year for this one. And then last problem number 18, calculator active problem. If f prime of x is equal to sine of e to the x and f of 0 is equal to 5.7, then what's f of 2? Well, I noticed that I've got these two limits of these two numbers going from 0 to 2. So I know that if I took the integral from 0 to 2 of this f prime of x dx, that by the fundamental theorem of calculus, that if I take the antiderivative of f prime, I'm going to get f, and I'm going to need to plug in 2 first. So f of 2 minus the other limit of integration, f of 0. So plug in what we know. That's the integral from 0 to 2 of this sine of e of x dx. That's equal to f of 2, which we're trying to find. That's the goal. That's what we want. I'll put it in green. That's what we want there. Minus f of 0, which they told us was 5.7. So what I can do, because this is a calculator active problem, is I can actually use my calculator, the features on the calculator, to hit math and then 9 to pull up that integral on my TID3 or TID4 to find the value of this integral. So f of 2 is going to be equal to 5.7 plus this integral, which we can put into our calculator, of sine of e to the x dx. I would do that, hit math, and then 9 for that fn int feature, type in this integral, get that value, add 5.7 to it. You should get, what do we get? 6.251 if we round to 3 digits after the decimal place for that. Good practice for you. But that's it. That's the practice. I encourage you to go back and review, come to class with any questions that you've got, or stop by office hours. Good luck reviewing, and good luck on your Chapter 6 test. Have a great rest of your day.